Welcome back, Ninja. Today we've received a scroll straight from Kakashi-sensei. And no, it's not a mission to spy on the Akatsuki. It's even tougher. Find the count of good integers, LeetCode 3272. You're given two numbers, n and k. Your mission: find how many n-digit integers can be rearranged to form a palindrome that is divisible by k. Reminder: a palindrome is a number that reads the same forward and backward, like 2002. But here's the ninja twist. The digits can be rearranged first. Oh, and no ninja cheats. No leading zeros allowed. Example: if n equals 5, k equals 6, then 24042 is good because it's a palindrome and divisible by 6. But 210112? Nah, not divisible by 6, so it's out. So, how do we generate all palindromes of n digits? How do we check if digits of a number can be rearranged to form them? And how do we avoid leading zeros? Sounds troublesome, right? Let's make it simple. All right, young shinobi. Before we jump into battle, let's sharpen our kunai and understand the concepts we're using here. And trust me, these are some of the coolest jutsu in the DSA world. Backtracking. Think of it like shadow clone jutsu. Imagine Naruto trying different moves until he finds the one that works. That's backtracking. In code terms, we're recursively trying to build a number, digit by digit, from both ends because we want to build a palindrome. That means, if we place a digit at index I, we also place the same digit at index n minus 1 minus I, mirrored. We start with an empty number like 000, and slowly fill in characters like 11, 22, until the whole thing is filled. At each complete number, we check, is it divisible by k? If yes, it's a valid warrior in our army. Combinatorics, Shikamaru's way of counting possibilities. Now imagine you already have a valid palindrome, let's say 5 and 25. You want to count how many different ways you can rearrange those digits, like 255, 5 and 52, 5 and 25, etc. That's where combinatorics steps in. If there are n total digits, there are n permutations. That's n factorial, meaning n minus 1, and then 2, stu 1. But if digits are repeated, we divide by their repetitions. Like if two digits are the same, we divide by 2. So we don't overcount duplicates. And one last ninja trick, we avoid leading zeros, because numbers like 0 and 11 are not valid integers when the leading digit is 0. So now you know, backtracking builds the numbers, and combinatorics counts the ways to rearrange them. Alright, team. This one looks like a mess at first glance, but as always, if we slow down and think a little smarter, we'll outplay the chaos. We've been asked to count how many integers of length n are, palindromic, that is, the same forward and backward, divisible by k, and we must consider all permutations of the digits in these palindromes as long as they don't start with a 0. Classic Jonin-level trickery. But here's how we'll break it down. Step 1. Generate all palindromes of length n. We start by generating every possible n-length palindrome, digit by digit. We'll use backtracking, which basically means try a digit on the left, mirror it on the right, then move inward until the number is fully built. This saves chakra. We don't need to check every number. We build only those that are palindromes by nature. But one thing, we skip numbers that start with 0 unless n equals 1. Step 2. Only keep palindromes divisible by k. Once we have our palindromes, we check each one, is it divisible by k? If it is, we keep it. If not, we discard it. Simple. Let's say n equals 3 and k equals 5. Some palindromes like 525 and 555 are divisible by 5. Others, like 535, are not. So we only move forward with the valid ones. Step 3. Convert each valid palindrome into a digit frequency pattern. Now for the clever part. Instead of storing the entire palindrome, we store a frequency pattern. Basically, how many times each digit appears. Why? Because we care about permutations. And permutations only care which digits are there, and how many times, not their order. So 525 and 255 have the same digit frequency pattern. Digit 5 appears 2 times, digit 2 appears once. So both are counted under the same pattern. It's like giving them a DNA signature. We use a string pattern to uniquely represent each digit frequency. Example, we turn counts into characters like A for 0 times, B for 1 time, C for 2 times, and so on. So this pattern becomes something like ABAASC, depending on the counts. It's weird looking, but it helps us group similar palindromes together quickly, no duplicates. Step 4. For each unique pattern, calculate the number of valid permutations. Once we have our unique patterns, we calculate how many distinct permutations we can make from that digit count. Let's say again, for 525, total digits equals 3, digit 5 appears 2 times, digit 2 appears once. Total permutations equals factorial of 3, divide by factorial of 2 for 2 5s, and factorial of 1 for the single 2. So we get 3 factorial divided by 2 factorial times 1 factorial equals 6, divided by 2 times 1 equals 3 permutations. So that one-digit pattern gives us 3 good integers. Step 5, remove permutations that start with 0. But wait, not all permutations are valid numbers. Any permutation that starts with 0 is invalid. It's not a real integer, so we remove those. We do this with a little math trick. Calculate all permutations starting with 0 and subtract them from the total. This keeps our final count honest and precise. Step 6, add up all valid permutation counts. Now we just sum up all the valid permutations from all valid palindromes. And boom, we have our answer. Efficient, tactical, quietly powerful, just like Shikamaru himself. All right, Shinobi, time for the real mission. This isn't a one-digit warm-up anymore. We're going full Genin-level logic now. Let's slow it down and break it step by step, just like how Iruka-sensei would explain something to Naruto in class. We'll take a real example and dry run the whole code to make sure we understand how everything works and how the final answer is calculated. Here's our mission. Input is n equals 3 and k equals 5. We need to find how many 3-digit integers can be rearranged to form a palindrome that is divisible by 5. So let's start from the top. A 3-digit palindrome looks like this. The first and third digits have to be the same, and the middle one can be anything, like 525, 343, 111, as long as the number reads the same forward and backward. We'll go ahead and generate all such palindromes. First digit goes from 1 to 9. Because a number can't start with 0, that'd just be a 2-digit mess. Then the second digit goes from 0 to 9, and the last digit just mirrors the first. That gives us palindromes like 101, 111, 121, all the way to 999. Tons of them. Now, we only want the ones divisible by 5. And here's the trick. A number is divisible by 5 if it ends in 0 or 5. But wait, we already know the first and last digits are the same. That means we're only looking for palindromes where the first and last digits are both 5. Because if they were both 0, it would start with 0, which isn't allowed for a 3-digit number. So we get valid palindromes like 505, 515, 525, 535, all the way to 595. Okay, we've got our valid palindromes. Now we look at each one and break down how many times each digit appears in it. Why? Because if some other number has the same digit frequencies, we can rearrange it to form a valid palindrome. Let's take 5 and 25 as an example. It has 2 5s and 1 2, so we note digit 5 appears twice, digit 2 once. Same thing with 515, 2 5s, 1 1. We record these frequency maps. Now we store all the unique frequency maps. We don't care what the number actually was. We care about how many unique digit sets can create a palindrome divisible by 5. Now comes the math jutsu. For each digit frequency set, we ask, how many ways can we rearrange these digits to form a 3-digit number? So for 525, which is 2 5s and 1 2, there are 3 digits in total. We calculate 3 factorial, which is 6. But since 5 appears twice, we divide by 2 factorial to avoid duplicates. That gives us 3 valid rearrangements. We repeat that for all other digit sets. Let's say we find 9 unique frequency groups, and each one gives 3 permutations. Then 9 times 3 gives us 27. And that's it. The final answer. 27. You made it to the end of the battlefield. We started by finding palindromes, filtered them for divisibility, broke them down into digit sets, and calculated all the valid rearrangements. Shikamaru might say it's troublesome, but you just crushed it like a true shinobi. One last mission before we wrap this up. Let's analyze how long this jutsu takes to execute and how much chakra it consumes. It's time for time and space complexity. We're generating all palindromic numbers of length n. Here's the interesting part. When building a palindrome, we don't need to generate all n-digit numbers. We only need to fill half of the digits, because the other half is mirrored. If n is 3, we only need to fill up to the middle, which is the ceiling of n divided by 2 positions. This gives us approximately 9 times 10 to the n the power of ceiling divided by 2 minus 1 possible palindromes. The number 9 comes from the fact that the first digit not be 0. The rest of the digits, including the middle one, can be from 0 to 9. For each palindrome we generate, we perform a few steps. Check if it is divisible by k. This takes constant time, big O of 1. Count the digit frequencies. This takes big O of n. Convert that frequency map into a unique pattern string. Since we only have 10 digits, this is constant time, big O of 10. Store it in a set, on average, constant time, big O of 1. So the total time complexity becomes big O of 9 times 10 to the power of ceiling of n divided by 2 minus 1 multiplied by n. Now let's talk about space complexity. We store all valid palindromes. Let's call that number p. P is approximately 9 times 10 to the power of ceiling of n divided by 2 minus 1. For each palindrome, we store a digit frequency map of size 10 and a unique string pattern. We also store all these in a set to avoid duplicates, so the total space complexity is big O of p. That wraps up the analysis. From building palindromes to counting valid permutations, every step was optimized with precision. This was all about pattern recognition, smart constraints, and avoiding brute force. You've completed the mission with the calm and clever thinking of a true strategist. The next challenge awaits. Stay sharp and believe it.